to a little bit of geometry. And so the problem is, they ask, what is the perimeter of a patio that is a rectangle? "18 feet on one side and 27 feet on the other." So I first draw my rectangle and 18, 27. Whenever I have a word problem, if it's something physical, I'll try to make a little drawing of it. And a rectangle is there. So there's information the book is asking us to know in here. And this information isn't always taught. So the book highlights these type of problems at this point so we can get a discussion on geometry. Rectangles are four-sided, with the sides opposite to each other being exactly the same. So that side's 27 and that side's 18. Now the perimeter would be the distance if I walked all the way around, or it's the total of all the sides. So to find this perimeter, I have to add 27, 27, 18, and 18. I have to add all the sides. Right? So perimeter, you add all the sides. Now, we'll find later that we can multiply 2 times 27 plus 2 times 18. We can do it as multiplication. But the book, because it's focusing on additions, doesn't show it this way. But what we want to do is we want to collect some of these ideas. And so the thing to remember is perimeters is the total of all the sides. And so in this case, 7 plus 7 is 14. 14 plus 8 is 22. And 8 plus 22 is 30. So I get a 0 here, and I carry my 3. All right. And then 3 plus 2 is 5. 5 plus 2 is 7. 7 plus 1 is 8. 8 plus 1 is 9. And the perimeter is 90 feet. I just wanted to point out that some of the word problems are there so that we start talking about things that will come up later. And this happens within this textbook quite commonly. All right. Whew. Well, so we have an algorithm for addition and subtraction. We have a reason that place value matters. The tool of place value helps us add and subtract without having to use external calculation tools. And so what we're going to do is we're going to add sorry, I didn't mean for the bad pun there. I know I'm a dad, but dad jokes are not my things. We're going to increase the algorithms we have by including into this. Fix this here. Sorry, I'm saving this because I ran out of blackboard space. Let me see if I can clear this. Yep, good. I'm erasing my blackboard here. Let me get a clean board and then I'll start talking because just doing this is distracting me a bit. There we go. There we go. We're working on things that we call operations. And operations are common ways that we talk. Operations. And the ones we have so far are addition and subtraction. And they all kind of reference back to the idea of counting. But what we want to do is we want to kind of look at our other operations. And so right now we're going to look at multiplying. Again, our general job is developing algorithms to do these with whole numbers, because we're going to take that algorithm with whole numbers and we're going to use it for the other numbers we do. Now, multiplying rows, the really first records of it were in Babylonian culture. When they first started doing agriculture, they would plow a field back and forth. And each row could produce so much crop. And so if you wanted to say how much crop you were going to get, you could go and you could count each plant. Right? Well, that'd take forever. There's acres of this. Or you could go, well, there's 1, 2, 3, 4, 5, 6 in this row, 6 in this row, 6 in this row, and 6 in this row, and you could add it up. Well, I'm adding the same value multiple times. Notice the word multiple in there. And so we invented multiplication to say, I'm taking the number 6 and I'm adding it. Now you're going to see I try to use the dot for multiplication so as not to confuse it with the x when we do algebra. And so how many times did we add it? 1, 2, 3, 4. Because there were 4 plowed rows. And 6 times 4 is 24. Now, back when we talked about the number systems yesterday, I said that this particular system of base 10 meant that there are only 100 things we needed to memorize. 50 additions and 50 multiplications. Memorizing your multiplication table will save you loads of headaches. If you haven't memorized it, and it used to be a more common thing that people had to memorize multiplications. With the advent of calculators and the No Child Left Behind curriculum, a lot of people have not memorized their times tables. If you are going to go into any medical field, these you need to memorize, because you're going to have to do mental calculations quickly. And if you haven't memorized them, a good flashcard system can get there. Even if you haven't memorized them, getting the grid, and let me pull the grid up here. Let me pull it up. See if I can get this to show up on the screen here. It's always the big plus. Where did I put that grid? Yeah, here it is. Let me put this on the screen for you. Go to my browser. This grid that I made here is called a multiplication grid. And let me make it bigger. See if I can make it bigger. Blackboard does not always allow me to do that. There we go. So if we look at this grid and I want to multiply 3 by the number 8, I come across 3 here and down from 8, and the answer is 24. Even if you're not going to be working in a field where you have to do mental maths and you don't need to memorize this, you should get in the habit of using a grid over a calculator, because it'll help you recognize the patterns that come up. And there are many times when we will be working with a bigger number, and you need to at least have the feeling that 6 times 8 is 48. Right? 6 times 8 is 48. And so I strongly recommend while doing these first 6 chapters, to only use your calculator to check yourself and try to use a multiplication grid and an addition grid to get a feel for the memorization of these things. You will find it makes things pay off a lot more. And there are some things that if you don't get a sense of memorization from it now, will be much harder later on when you go to do it. In fact, in an in-class version of this class, the first 2 exams are calculator free. So, but I do give a multiplication table. And that's how you get used to the algorithms. These algorithms we're doing with numbers right now will come back up in algebra, so being able to manipulate the number is important. But, so now we have this idea where yet again, people had collections of things that were all the same. And when they brought the collections together, instead of counting them and instead of adding, they invented a new shortcut called multiplication. So each one of these collections has 3 things. So it's 3 times, how many collections do I have? 1, 2, 3, 4, 5, 6. And 3 times 6 is 18. And so the game that human beings have been doing was, we're going to count things. Well, that's too hard. We're going to add them so we don't have to go back, and when I have 5,321 things, I don't have to count each individual thing when I add it to it. I have this algorithm of addition, but underneath it all, the quantity is still counting the individual things. And then people said, every time I'm doing this, I put in 3 things. And those 3 things keep repeating, so I'm adding 3 over and over again. Well, we're going to call that multiplication. But underneath it all, the quantity is still adding up. And so mathematics is a load of laziness, right? We don't want to sit there and count every individual thing. We want to use the rules and patterns of quantity to make it easier for us to find answers to them. But underneath it all, everything adds up. And once everything adds up, we count it. So most of math, in its essence, is counting somewhere, somehow. We just do a little shortcut from it. And you'll find every time we introduce a new symbol, we're really making a shortcut for an older symbol. So addition was a shortcut for counting loads of things. And multiplication, which I'll write as an X for now, but I'll usually write as a dot, is for adding the same thing over and over. All right. So you could kind of think of math as like a laziness. We're giving symbols to help us work our way through. A little bit of a warning. It looks like I have a bit of a thunderstorm rolling through. So if you hear any thunder, it is what it is. All right. Well, the property of real numbers also worked for multiplication, and the identity for multiplication is anything times the number 1 is itself. Multiplication also has a 0 property, which is any number times 0 is 0. And I want to kind of think of that conceptually. If I'm adding the same things over and over again, if I only add it once, I just have that thing. But if I add it 0 times, well, I never even started, did I? So I'm stuck with nothing. And multiplication also commutes, it's commutative. So it doesn't matter the order I multiply in. Right? 3 times 2 is still equal to 2 times 3. It's also associative. I have a chain of things I'm multiplying together. it doesn't matter which ones I multiply first. So if I have 3 times 4 times 5, and I say I'm going to multiply these first, 4 times 5 is 20, and 3 times 20 is 60. Well, someone else can, you know what, I'm going to multiply 3 times 4 first, times 5, and that's 12. Well, 5 times 12 is 60. Remember, these things at the end are talking about counting up stuff. So the order shouldn't matter in how we count it. These commutative properties and these associative properties are kind of like saying, well, does it matter that I start counting from the left or from the right? All right. Well, we are going to have an algorithm that works like addition for multiplication, and place value is used. So if I have 76 times 6, well, I can think of 76 as 70 plus 6 times 6. And if we look back on that property of real numbers, right? Remember the property of real numbers I said it was going to come back? We have a distribution property. And that tells me that 6 times 70 plus 6 times 6 is equal to this. Because I can distribute this to each part. And 6 times 70 is 420. And 6 times 6 is 36. And I add those together. I get 456. Well, I don't want to break everything apart with distribution. I don't want to write in the expanded form each time. This is why it works. But how we do it, to make it easier for ourselves, is we, again, write the numbers vertically, letting the place value hold things together. So 6 times 6 is 36. That goes in the 1 place with an additional 3 coming here. 6 times 7 is 42 plus that additional 3. And so the place value does all of this work for us. And so the algorithm for multiplication lets us have place value keep track of things for us. And so we always start in the ones, multiply the ones, carry over any extra digits, and add it to the next multiplication. It's the same as this, but in a format that's easy to manipulate. Let's look at a couple of these. Let me pull one here. Let's see. Yeah. All right, I'm going to do an ugly one. For what happens, I'm going to do 423 times 6. For some reason today is multiplying by 6. Now notice, I am multiplying this by a number less than 10. So I go 6 times 3 is 18. I bring the 1 over here. 6 times 2 is 12, plus the 1 is 13. 6 times 4 is 24, plus the 1 is 25. And I got 2,538. So our algorithm keeps track of the number for us and keeps us moving. Well, what happens when this number is larger than 10 or larger? So I'm going to look at 412. I'll go really bad at 198. Now I could take all of 198 and multiply it by 2. Then I'd have to do 2 times 8, 2 times 9, 2 times 1. And then I take all of 198 and multiply it by 1. And I take all of 198 and multiply it by 4. And I would get this really big jumble of stuff coming out. But place value helps us. So I start on the lower digit, the bottom rightmost digit. And I just look at the 8. And I'm going to take my answers and I'm going to leave them on separate lines. And I'm going to line up my answer directly below the 8. Just like I did here, I started my answers directly below the 6. So 8 times 2 is 6. And I carry my 1. 8 times 1 is 8, plus the 1 is 9. 8 times 4 is 32. And so I've finished the 8, so I'm going to change color here. This is done. And now I'm going to look at the 9. I moved left across my lower digits. And I'm going to line up my answer below the 9 down here. So 9 times 2 is 18. And I carry my 1. 9 times 1 is 10. So I carry my 1. 9 times 4 is 36. Plus the 1 is 37. So notice how place value is holding position for me. All right, I have one more digit to go, which is the 1. Again, I'm going to line up directly below, but on a new line down here. 1 times 2 is 2. 1 times 1 is 1. And 1 times 4 is 4. Now, some people learned to fill in these places with zeros. I was always taught to line directly below the thing you're doing, and so those zeros were kind of implied. Other people sometimes need to put the zeros in to keep track of it. Neither is right or wrong. Notice we're just keeping track of the things we do with the place values. So 6 plus 0 is 6. I'm going to add up all of my answers. 9 plus 8 is 17. Carry my 1. 2 plus 2 plus 1 is 5. 3 plus 7 plus 1 is 11. Carry my 1. And 3 plus 4 is 8. I've got 81,576. Imagine you have 412 rows that carry 198 plants. You go out and you count each one, you would have to count 81,576. It would take a while. But if you counted one row and you counted your number of rows, you could do the calculation. This is what mathematics do. They take a very complex operation, but they look for any time there's a repetition or a pattern in it, and they use that pattern to get the answer more quickly. And for us, all of the information is encoded in the place value. The naming of numbers that human beings did with place value is what brings this utility for our calculations. Now, I'm only doing 1 or 2 examples in the lecture. I will post 1 or 2 additional examples. If there's any examples that you personally want to see, email me. Alright, I'm trying to open because I want to do one more thing. We noticed